Properties of logarithms. One of the reasons that logs are used so often is their unique properties. Since logs are an inverse of exponents, it's not surprising that the properties of logs are related to and can be derived from the properties of exponents. First, let's examine the basic property of any inverse function, then we can revisit the properties of exponents. Inverse operations undo the effect of the original. Subtraction undoes addition, so x plus y minus y equals x. Addition undoes subtraction, so x minus y plus y equals x. Division undoes multiplication, x times y divided by y equals x. Multiplication undoes division, so x divided by y multiplied by y equals x. Taking the root undoes raising to a power. X squared raised to the 1/2 power equals x. Raising to a power undoes taking a root, so x to the 1/2 power to the 2nd power equals x. Taking the log undoes raising to a power. Log base a of a to the power of x equals x. Raising to a power undoes taking the log. A to the log base a of x power equals x. Here are properties of exponents. A to the m times a to the n equals a to the m plus n. A to the m times b to the m equals a times b to the m. A to the m to the n equals a to the mn. A to the 0 power equals 1. A to the 1st power equals a. A to the m power divided by a to the n equals a to the m minus n. Exponent property. A to the 0 power equals 1. First, let's take the log base a of both sides. Log base a of a to the 0 power equals log base a of 1. Since logs and exponents undo each other, how can we simplify the left side of this equation? Well, they undo each other, so we can cancel the log out and this a. So we're left with 0. 0 equals log base a of 1. So there's our log property. Log base a of 1 equals 0. Exponent property, a to the 1st power equals a. First, let's take the log base a of both sides. Log base a of a to the 1st power equals log base a of a. Since logs and exponents undo each other, how can we simplify the left side of this equation? Well, the log base a cancels out with the a, leaving us with 1. 1 equals log base a of a. So that's our new log property. Log base a of a equals 1. Exponent property. A to the x times a to the y equals a to the x plus y. First, let's create log equivalents of the terms on the left side. A to the x, we're going to set equal to m. And that will be log base a of m equals x. We're going to set a to the y equal to n, which is log base a of n equals y. Their product is m times n, which is a to the x times a to the y equals a to the x plus y. So now it's going to be m times n equals a to the x plus y. Now take the log base a of both sides. Log base a of mn equals log base a of a to the x plus y. So these cancel, leaving us with just x plus y. Substituting for x and y yields log base a of m times n equals log base a of m plus log base a of n. So the log property is log of base a of m times n equals log base a of m plus log base a of n. Exponent property a to the x divided by a to the y equals a to the x minus y. First, let's create log equivalents of the terms on the left side. A to the x equals m. So we have log base a of m equals x. A to the y equals n, therefore log base a of n equals y. Their quotient is m divided by n, which in this case would be a to the x divided by a to the y, giving us a to the x minus y. So we have m over n equals a to the x minus y. Now take the log base a of both sides. Log base a of m divided by n equals log base a of a to the x minus y. So these cancel, leaving us with just log base a of m divided by n equals x minus y. Substituting for x and y yields log base a of m divided by n equals log base a of m minus log base a of n. So there's our new log property. log base a of m divided by n equals log base a of m minus log base a of n. Exponent property a to the x to the y equals a to the xy. We have shown that log base a of m times n equals log base a of m plus log base a of n. Therefore, log base a of m to the n can be written as log base a of m times n, etc., with m multiplied by itself n times. Using the above log property, this repeated multiplication on the left becomes repeated addition on the right side. Log base a of m plus log base a of m, and so on, with n terms of log base a of m. Repeated addition is just multiplication. Therefore, we have n times log base a of m. Setting the right and left sides equal yields the property log base a of m to the n power equals n times log base a of m. Here's a summary of the properties of logs. Log base a of m times n equals log base a of m plus log base a of n. Log base a of m divided by n equals log base a of m minus log base a of n. Log base a of m to the n power equals n times log base a of m. So you can just take this exponent and move it out front right there. Log base a of 1 equals 0. Log base a of a equals 1. Log base a of a to the x power equals x, because these cancel out. And a to the log base a of x equals x, because these cancel out. Since natural logarithms only differ with a base of e, the same properties apply. To solve equations and use a calculator for bases other than 10 or e, we need an approach for finding the logarithm for any base. The next slide shows how we can derive a formula for this purpose. Remember that log base b of x is asking b raised to what power will equal x, or find y when b to the y equals x. So we start with log base b of x equals y. We're going to rewrite in exponent form. So b to the y equals x. Then take the log base a of both sides. Log base a of b to the y equals log base a of x. Use this property of logs, so we're going to take this exponent, move it out front. So we take this y, move it out front, so we have y times log base a of b equals log base a of x. Then we solve for y. So divide both sides by log base a of b, and we get log base a of x over log base a of b. This is the change of base formula. Since common logs, base 10, are programmed in calculators, we can use this form of the change of base formula to evaluate other logs. Try using your calculator to find log base 4 of 25. Using the formula, log base 4 of 25 can be rewritten as log base 10 of 25 divided by log base 10 of 4, which you can actually put into your calculator with the log button. So that equals about 2.322. Is this a reasonable answer? Since 4 squared equals 16 and 4 to the third power equals 64, it seems reasonable that 4 to the 2.322 power would equal 25. You can check the result with your calculator. When using a calculator, be sure to use parentheses correctly. The division problem above can be typed as log parenthesis 25 close parentheses divided by log open parentheses 4 close parentheses. Properties of logs can also be used to expand and condense expressions. Expanding and condensing logarithm expressions are used often when solving more complex equations. Before solving equations, we need to practice these skills. Use the properties of logs to expand log base 4 of m squared times n. Because we have m times n, we can separate those into two separate terms, log base 4 of m squared plus log base 4 of n. Then this exponent can be brought out front so that we have 2 times log base 4 of m plus log base 4 of n. Use the properties of logs to expand. Since we have 3m divided by n to the fifth, we can write this as log of 3m minus log of n to the fifth. Then we can separate 3 and m into two separate logs, log 3 plus log m. and then we have minus, and then we can bring this 5 out front, so we have minus 5 log n. Over here we have 1 divided by mn to the fourth, so we can change this from a fraction to be 2 logs with a subtraction. So log 1 minus log of mn to the fourth. So this exponent can be brought out front, log 1 minus 4 times log of mn. Then this multiplication can be separated into an addition. So we have 4 times log m plus log n, and then we can distribute that negative 4 to both of these terms. So we have negative 4 log m minus 4 log n. Use the properties of logs to expand. Here we have 10 times m to the fourth times n cubed. So we can separate this into 3 different terms all added together. Then we can move these exponents out front. So we have the natural log of 10 plus 4 times the natural log of m plus 3 times the natural log of n. Here we have a division, so we can break that into a subtraction. The natural log of 6n to the fourth minus the natural log of m cubed. Then we have 6 times n here, so we can break that up into an addition. So the natural log of 6 plus the natural log of n to the fourth, and we still have this minus natural log of m cubed. Then we can bring this exponent out front, giving us the natural log of 6 plus 4 times the natural log of n minus 3 times the natural log of m, since we've also moved that exponent out front. Properties of logs can also be used to expand and condense expressions. Expanding and condensing logarithmic expressions are used often when solving more complex equations. Before solving equations, we need to practice these skills. For example, use the properties of logs to rewrite as a single log. So we're going to be undoing what we've been previously doing. So instead of moving an exponent down front, we're going to take a number, a coefficient out front, and make it the exponent. So this 2 becomes n squared. It moves up there. Then we have log base 3 of m plus log base 3 of n squared. So we can combine these into this, m times n squared. Use the properties of logs to rewrite as a single log. Alright, so the first thing we're going to do is make all of these coefficients into exponents. So they all go up top like that. Now we have an addition and a subtraction. So the subtraction will create this fraction here, where this goes on the bottom, the denominator, and the x to the fourth times y to the third will end up in the numerator. Over here we have negative log b, so this negative 1 becomes the exponent. So we have log of b to the negative 1 power, which means that we could rewrite this as 1 over b. Use the properties of logs to rewrite as a single natural log. First, we move our coefficients into exponents. So we have the natural log of x squared plus the natural log of y cubed. So this is an addition, so then we can take what's inside the parentheses and multiply it together. Over here, first we move our coefficients into the exponent positions, and then we can create a fraction like this. We have a negative natural log of y cubed, so this will go in the denominator. And then we have the natural log of x to the fourth plus the natural log of z, so we can multiply x to the fourth and z together and put it in the numerator.